Okay, what we've got is a coil of wire here, and we have a galvanometer, and a galvanometer is essentially an analog current device that measures current both directions. So it can measure current flowing through a circuit one way, and it will measure current flowing through the circuit the other way. So I've got my galvanometer hooked up to the ends of this coil of wire. And what we want to do is we want to demonstrate an example of Faraday's law. And Faraday's law tells us what will happen when a complete circuit like this one has a area, right? And so you can see that there's a circular area here through which a magnetic flux can propagate. And under the condition that a magnetic flux can propagate through the area of a circuit, Faraday's law tells us that there will be a generated electric field. And when you generate an electric field in a complete circuit, you will generate a voltage through the circuit, and when you generate the voltage through the circuit, you will generate a current through the circuit. So this is the basic idea of Faraday's law. So I have a magnet here, just basic bar magnet, and watch what happens to the galvanometer needle as I pull the magnet toward and away from the coil, right? So the needle deflects one way when I put the magnet toward the coil, and when I hold the magnet still, effectively the current goes away, and when I pull the magnet out, the needle deflects in the opposite direction. Okay? Now, the north and south markers on this magnet have worn off, and so I'm not exactly sure which is which. I believe the red is north and the blue is south. And so just take note that when I'm using the red side, right, when I'm using the red side and I put the magnet in, the needle deflects one way, and then when I pull it out, it deflects the other way. If I reverse the magnet, when I put the magnet in, the needle deflects the opposite direction, and then it deflects the opposite direction out. And so what is this telling us? This is telling us a few things. Number one, notice, once again, what the current does when the magnet stops moving. So the magnetic field has to be changing some way for the current to be generated here. Okay? The magnetic field has to be changing in some way. If I produce a static magnetic field, nothing happens. And you can even get this effect to an extent outside the wire, because the magnet itself has a magnetic field, and that magnetic field, some of it is penetrating into the coil, and so there will still be some effect of this, but it's most strong when the flux through the coil is maximized. And so that's why putting the magnet inside maximizes that deflection. And once again, the direction of the magnetic field is important. If I put a magnet oriented one way in first, the current will deflect one way. If I put the opposite end of the magnet in first, it will deflect the opposite direction. And also, the strength of the magnetic field matters. So what I've got here are two neodymium magnets that are attached to a bar magnet. And these are very, very strong magnets, very strong magnets. And when I pull this over, you can see the deflection is a little bit bigger than what it was when I ran the initial bar magnet just over the surface. And now watch what happens when I put the neodymium magnets in. Okay? So the direction of the magnetic field matters. for the direction of the current. The strength of the magnetic field matters in terms of the magnitude of the current, and the speed affects the rate at which it alternates. Okay? Now, this is not the only way to generate this, but it's a very striking way to generate it. And you'll also notice that the faster even just the simple bar magnet, the faster I pull it out, the faster I pull it in and out, you'll see that the magnet or galvanometer needle deflects much faster, even if it doesn't deflect with the same magnitude of the neodymium magnets. This is a very strong magnetic flux through this coil, okay? And again, you don't even have to be inside the coils. And let me see if I can show this in the shot. We'll see. Yeah, so let me move these out of the way. Move this in, okay? And in fact, let me do this first. Okay. All right. So you don't even have to be inside, as I said before. And here you can see the galvanometer needle moving back and forth, right? And in fact, if you do this hard enough, you'll actually start to feel the magnetic repulsion between the neodymium magnets and the magnetic field generated by the coil here, okay? So this is examples of Faraday's law of induction, and the next videos will be some lectures on the topic and how we describe it mathematically.